How's it going?
Could be better.
Could or couldn't?
Could be better.
Could be better. I think that's probably always true, though. So questions? Yeah.
Just a random question, but what is strtok? I found it somewhere online, and because I was looking for ideas, and someone suggested that as a way to parse data.
So strtok sounds like string tokenizing. So tokenizing is a way to take a set of input and turn it into sort of uniform things that you recognize, kind of like diagramming a sentence. So you might take a set of input and say this is a weight, and this is a value, and this is a name, right? And that's what we do with scanf, for example. And we don't need anything that fancy because our input file, knapsack.data, always has the same format on every single line. But if it could have different formats, then you'd need to sort of break it into these tokens, right? These lower level identifiers, so that you could say, okay, this is 2 integers followed by a string. That must be the description of an item, or this is a semicolon followed by a string. This is a comment, that kind of thing. So I didn't get a chance to read your email, but is it a question that you can ask here? It has something to do with the input file, I think, right?
Not necessarily. It's how I'm trying to scan in the information. I used a scanf to try and scan it in, but when I'm printing out the data, it gives me the wrong weight and value until the very end.
Interesting.
I included all the relevant information regarding what happened.
Well, let's just look at this in general. Bless you.
So were you working on reading?
So this was our practice code from yesterday, right? So we're reading in a line. So let's play with scanf. And I don't know what comes first. I'm gonna guess weight.
I explained in that email, I think the error lies within how I'm passing the information back between functions.
Ah, okay. Okay.
And I'm messing with a global variable, which is may also be part of the problem.
So if you do a scanf like that, that should fill up weight, value, and name with the pieces of each input line. So this would not be my main program. This would be something like, read the input file or something like that, and I would take these things and I'd load them into an array or a series of arrays, right, and then pass back that array or make that array global maybe. All right, well, I can look at your code in the email later and respond to that. Yeah.
Is weight to 0 a valid weight and value?
For the input file? If your weight is 0, you're going to get a max val of infinity. So I would say no, don't allow weight of 0.
Okay. That sounds good to me.
Yeah. Because if something weighs nothing and it's got any value, you can just keep putting more and more of it in your bag and get more and more value. Kind of like the U.S. economy or something.
We go for the coding part for the main algorithm. It's going to be recursive of calling max value and putting the global, multiple versions of the global, like possible max value or something like that, and comparing those.
Basically, yeah, not global, but yeah, let's go through that algorithm. And I'm going to stop talking at 11:35, and I'm going to take off, and I'm going to give you 15 minutes to On Canvas, you should have an item you can fill out, which is an evaluation of me. Have you seen that?
I've done that.
Okay. How many people have done it already? Oh, okay, most.
Been
All right.
bugging us for about 2 weeks.
Okay, cool.
I haven't done the other evaluations though.
Yeah, so if you're in 215, you have an option for that one also. So I'm going to bug out early and give you a chance to work on that. And you can do that on your laptop if you're here, or you can go to the collaboratorium and do it on one of the machines in there. But I really want to get as close to 100% on that as possible. 100% participation, because that's important feedback. All right, so let's look at this algorithm. So you have an inventory, you've got weights, and you've got values, right? And these are stored in arrays of some kind, parallel array structure or something like that. And so let's say we want to find max val of some capacity. And we need to know how many items we have. So that's how many things we have in these arrays. So you figure that out when you're reading your knapsack.data file. You just remember how many things you read in and saved. So we're going to have some kind of loop. So from 0 up to the number of items minus 1. So for all the items that you have in your arrays, well, if we put item I in our bag now has a value of whatever the value of item I is. And we're going to put more items into our bag in such a way that we get the most value out of that extra unused capacity that our bag has. So we put in item I first. The amount our bag can hold goes down by the weight of item I, and now we're just going to fill up the rest of that bag in whatever is the best way possible, right? What is the most value we can get out of that remaining bag? Well, our max val function tells us that. If we started with a capacity of cap and we lost capacity equal to the weight of item I, right, this expression is the most we can get by packing other stuff into our bag. And if we take that value and we add the value of item I, that's the value that we can get, the best value we can get if we start by putting item I in. So we need to remember what the best value is of all of these calculations inside this for loop. So it's like a running sum, it's a running max. So we can do something like best equals 0, and this is our best value so far. And then it's just if temp is bigger than best, then set best equal to temp. So when we come out of this for loop, best is our best value. And so we return best. And there's one more detail. Remember, we can't do this calculation if our item weighs more than our capacity. Right? Suppose we had an item that was worth $1 billion, but it weighed 100 pounds. Okay, $1 billion, but it weighs 100 pounds, and we're trying to find the max value we can get out of a 10-pound capacity. When we get to that item number, the value is $1 billion, right, plus max val of capacity minus weight, that's minus 90, right? If our max val just returns a 0 here, our temp's going to be $1 billion, and that's going to be our best value, and we're going to end up returning and saying the max value we can get out of a 10-pound bag is $1 billion, and that's not true, right? So if this is negative, we don't want to do this, right? We don't want to compare our temporary possible answer because it's not a valid solution, right? This is not actually a value we can get by putting in item I. because it'll break our bag. So you want to sort of preface this by if weight, bless you, if the weight of our item is less than or equal to the capacity, then you can do this. Calculate the possible solution from this, compare it to your best. And that takes care of the edge case where all your items weigh more than what your bag can hold, because none of these calculations will take place. Since you're initializing your best to 0, you'll end up just returning 0. And that's exactly the right thing to do. So does that middle piece of code make sense? So once you've got this and it's returning the max capacity, max value correctly, and you can run the sample code on the server to compare your solution for different inventories and different knapsacks. Once it's doing the right max value, then your challenge is figuring out how you get that max value. What's the inventory of items that you should put into your bag to get that max val? And that's a level of difficulty beyond this. But the algorithm is straightforward. So you're going to need to return not just a max val, but also how you got that max val. So my suggestion the other day was something like this. Return a structure result which has a value piece, that's just the max val, but then also an array of item counts. And we have a maximum of 128 items, so that can be an array of 128 ints. And then inside this loop, when you're doing this, this call to max val will return not just the maximum value, but also the collection of items that got you that max val. Okay, so every time we call max val, we get back 2 pieces of information. What's the maximum value, and how do we get that maximum value? Put in 5 of this item, and 2 of that item, and 3 of this other item. Okay, we need to remember not just the max val and temp, but we also need to know how we got that. Because at the end, we're going to adjust that optimal packing to get our optimal packing for our original capacity. So let me just do an example with totally bogus numbers, just to kind of illustrate that. So this is our bogus example. Alright, so here's an item number, here's a weight, here's a value. So we're just going to assume 4 items, and I don't know, weight of 1, 2, 5, and 8, and values of 4, and 9, and 22, and I don't know, 35. I'm making this up. Alright, so suppose we're trying to find max val of 15. So we're in our loop and we're going to perform 4 calculations inside our loop. One is assuming that we start with item 0. So item 0, we're going to calculate the value of item 0 plus max val of 15 minus 1, 14. Item 1, we're going to take the value of item 1, which is 9, and then calculate the maximum value of our capacity minus the weight of item 1, which is 2, that's max val of 13. Item 2, we're going to take the value of item 2 plus max val of 10. In item 3, we're going to take the value of item 3 plus max val of 7. So everybody comfortable with why I wrote down these 4 equations? Right, value of the item, max val of the capacity, minus the weight of that item. Okay, so our max val is going to return 2 things. It's going to return a value, and it's also going to return how we got that value. So it's going to return an array, well, a structure. So it's going to say value, and then it's going to have an item count. Which says how many of each item we got. Okay, so here's the totally bogus part, right? These may be completely physically impossible. I'm just making up some numbers. So suppose that when we calculated suppose I put these things down so they line up. Okay, suppose when we calculated item 0, we called max val 14. Suppose max val 14 returned the following. It said the way you get your maximum value is by having 1 of item 0 and 2 of item 1 and 0 item 3 and 1 item 4. Okay. And I think that comes out to 56. Don't worry if it doesn't add up. It's just an example. Okay, and suppose that for max val of 13, the way it got the maximum value out of that was to have 3 of item 2 and no items of the others, and so that had a value of 66. And max val of 10, the best we could do was to have 1 of item 1 and 1 of item 3, and that gave us a value of 44. And max val of 7, the best we could do was to have 7 item zeros and no other items, and that got us 28. So as we're going through these calculations, we're keeping track of what our best solution is. Okay, so our best solution starts off at 0. We find a 56 and we say, hey, item 0 gave us a 56, that's better. So our best index is 0. Our best value is 56, and the way we get that is by that collection of items. We do our second calculation, our value is 66. Hey, that's better. So now our best index is 1. Our best value is 66, and we get that by this inventory of items. We do our third calculation, 44, nope, that's not better. Do our fourth calculation, 28, nope, that's not better. We come out of our for loop. We know 2 things. We know the best value we can get is 66, so that's the value that our max val function is going to return. But we know that to get 66, we put in 1 of item 1, right, that's our best index. And then we got the maximum value out of the remaining capacity, and we did that by putting in this many of each item. So to get the best value for 15, we just take the number of items 1 that we had, which was 0, and we increment it. And so the inventory that we return is this collection of items, 0, 1, 3, and 0. And we say the value we can get out of that is 66. That's all there is to it, but it's tricky to get it set up just right. Mostly because you need to remember a lot of information. You need to pass around this result, right, or some way to pass around the number of items that max val said gives you the max value. And you need to know which, not just the max value and not just the inventory, but what item you added to get your final max value so that you can bump up the count of that item. Okay, but do this on paper and then write some code to do this in C. And it's really not bad once you sort of get it squared away mentally. But if you just start writing code without that picture, it can get confusing.
The way I did it on mine is when I read in the data, I stored basically I had a float and I calculated the value per unit weight. And then I just looped, and then I took the one with the highest value per unit weight, I'd put it in as my solution, and then basically looking at how much weight I can carry, I would store like the highest value per unit weight item that could fit into that space. Does that work out, or?
It will work sometimes, it will not work some other times.
Okay.
So are we good on this before I go on? So here's a counter example for that approach. So let's see. So capacity is 4, and here's our inventory of items, and so value per weight, this is worth $4 a pound, this is worth $10 a pound, this is worth $11.67 per pound. So what you're describing is called a greedy algorithm, right? It would say, okay, here's the most valuable one, let's take as much of that as possible. Well, it weighs 3 pounds, so we'll have item 3, $35. And we've got 1 pound left, so we'll put in item 1, $4. And we get $39 out of our 4 pounds. Right? A non-greedy solution is take 2 of item 2, and that's worth $40, and it still fits in your bag. So this is more valuable than item 2.
I was doing it by taking the unit, like value per unit weight. So I would have done like 35 divided by 3.
Right.
And then I would have used the and 2 as the highest value per unit weight. So I would have, in my algorithm, I would have taken 2.
But that's only 10 and that's 11.
Oh wait. That was not 20.
Yeah, so 20 value for weight of 2. So that's 10 per unit weight.
Oh, okay.
Right, and this is 11 something per unit wage. And the issue is, item 3 is more valuable than item 2. Item 1 is relatively worthless, right? And if you take item 3, you're forced to take item 1 to use up that extra 1 pound. And if you'd taken a little less value by putting in item 2, you'd have enough space to put in another one of it, and it ends up being a win. So if you're not restricted to integer amounts, if you can do fractional amounts, that works perfectly, right? Just load up from the most valuable item on down. With whole numbers, that fails in some cases. So then you got to get into the whole kind of recursive formulation. So other questions on knapsack?
Do you specify that we were only allowed to use one global variable?
No, I didn't specify. You don't need any globals except for the save array for the dynamic programming piece. That one is a whole lot easier if it's global. You can pass around the inventory of items as arguments, but I don't mind if you make that global, because that's something you set in the very beginning of your main program. You read in knapsack.data, and it's never going to change. It's just consumed. So if you want to simplify your functions, you can make that global. All right, let me mention a second dynamic programming. And this is almost the same as knapsack problem. This is rod cutting. And here's the idea. Picture a rod of material. It's a certain length. Let's say it's 5 inches. And you can sell this for this 5-inch piece of material, and somebody will pay you a certain amount of money for it. So if you sell a 5-inch piece of material, maybe it's worth 10 cents. But it may turn out that if you cut this into 1-inch lengths, that's more valuable to people, because most people don't have tools to cut this precisely. And so maybe a 1-inch length somebody will actually pay you 3 cents for. And from a purely economic sense, that doesn't make sense, right? Because you could buy a 5-inch piece for 10 and then cut that into 5 1-inch lengths yourself, right? But it's a service fee, basically. So if you pre-cut this into 1-inch lengths, you may be able to get 3 cents for each one, which means you could cut this entire rod into 5 pieces and get 15 cents instead of 10. And it may be that a 2-inch length is worth 5 cents, and maybe a 3-inch length isn't worth anything to anybody for some reason, and a 4-inch piece is worth only 2 cents. So you have some kind of pricing table which says for different lengths how much can I get, and your question is how should I cut this rod up to sell it for the most possible money. And there's always people who are willing to pay this to purchase your pieces of rod. So there's infinite demand. And it's like the knapsack problem, right? You can only cut it into these lengths, and you're trying to find the best possible value. And so we can define a max val of 5, and it's the largest of the following. Well, if we cut off a 1-inch piece to begin with, we can sell that for $3, and we're going to have 4 inches left. We could sell that as is, we could cut it into 2 2s, we could cut it into 4 1s, etc. There's different possibilities. The most we can get out of that 4-inch piece is given by the value max val of 4. Or we could cut off a 2-inch piece, sell that for 5 inches, and then find what the maximum value is from 3 inches, and so on. And if we start with a 5-inch piece, then we have nothing left to cut, so we have a max val of 0. And so this is just knapsack revisited, right? So make a loop, go through your pricing table, decrease your length by the length of the piece you cut, increase your value by that amount, and whatever the largest of those is, that's your max val of 5. Does that make sense? So this is a typical final exam question, where I might give you a pricing table and ask you to come up with something like this. So give this some thought, and we can talk about it more tomorrow if you like. But let me show you a different way that you can approach this problem that doesn't involve any recursion, which is to do the following. So first we can definitely state max val of 0 is 0. Right? If you don't have any material, you can't sell it for anything. So max val of 1 equals the largest of. Well, we can have the value of that 1-inch piece plus max val of 0, and that's really it. Right? If we have a 1-inch piece, our only option is to sell that 1-inch piece, which is going to be worth $3. So we know max val of 0, we know max val of 1. Max val of 2 equals the largest of, well, if we cut a 1-inch piece, that's worth 3, plus max val of 1. Or if we cut a 2-inch piece, that's 5 plus max val of 0. And at this point, we've already calculated max val of 1 and max val of 0. So this is 3 plus 3, which is 6. This is 5 plus 0, which is 5. The largest of those is 6. So now we know max val of 2. And if we write down the same equation for max val of 3, it's going to involve max vals of 2, 1, and 0, which we've already calculated. So we never really need to do any recursion if we start from the bottom and we work our way up. So this is another version of tail recursion, right, where the recursion's at the end of your code. You can turn it into a loop, basically. Okay, so don't do this for the knapsack problem, but it's an option. But I want you to do it recursively. And for a knapsack problem, since we don't have all possible weights in our table, there may be some weights we never have to calculate. If we're trying to find the max val for a capacity of 1,000 and our lightest item weighs 100 pounds, there's probably a number of weights we're not going to encounter. And there's some good number theory 215 stuff to figure out what we have to actually calculate. But if we just do it recursively, we only do the calculations we actually need. All right, let me give you a setup for what we'll talk about tomorrow. I'm still going to talk about red-black trees tomorrow, but let me give you a setup for another dynamic programming question, which is egg drops. So here's the basic egg drop setup. You have a building with a certain number of floors, and you have a basket of eggs, a certain number of eggs. So we'll say you have F floors, and you have E eggs. And somebody wants to know what's the highest floor you can drop one of these eggs from without it cracking. Okay, so all the eggs are identical. If dropping from a given floor cracks the egg, dropping from a higher floor will also crack it. If dropping from a given floor does not crack it, dropping from a lower floor will not crack it. And if you drop an egg and it doesn't crack, it doesn't change the egg at all. It doesn't become partially damaged. So if I can drop it from this floor successfully, I can drop it from this floor 1,000,000 times and it'll still be successful, and it'll still behave exactly the same as if I had never dropped it. So these are like idealized eggs. And somebody wants to know what's the highest floor I can drop an egg from, the eggs are identical, without the egg cracking. And your goal is to perform a series of experiments to answer that question. And you're going to charge based on how many experiments you have to do, because you got to go up and down floors and all this. So you want to be able to guarantee to the person the maximum number of experiments you need. Okay, and you may get lucky. You may go up to floor 17, drop an egg, it survives, go up to floor 18, drop it, and it cracks, and it took you 2 experiments. Okay, but you can't guarantee that. So what's your guaranteed number of experiments that you need to be able to answer this question? Say what?
The maximum number of floors?
Maybe. So if you have 1 floor, how many experiments do you need?
1.
Really just 1. You just drop it from that floor. If it cracks, then you've got your answer. If it doesn't crack, then you've got your answer.
Maybe like half of max number.
Maybe. So if you have n floors and you have 1 egg, how many experiments does it take? And that might be what you were... So how do you figure out what the critical floor is if you have 1 egg?
Can't you use the same method as like log or high-low?
So we got a building with 128 floors, and we got 1 egg.
Oh, only 1 egg?
Only 1 egg, yeah.
Oh boy.
So we're working on an edge case here. So how would you answer this question? How would you find out what the critical floor is?
You go to the middle floor.
Okay, so you go to floor 64 and you drop your egg and it cracks. And now you can't do any more experiments.
Start from the first floor.
So you got to start from the first floor, so that's n floors, right? So if you only have one egg, the answer is F. Right? Could take you, worst case, F experiments to answer this question, because you got to go one floor at a time. If you have 2 eggs, you can probably do better. So you could start with the middle, drop it at 64. If it cracks, now you've got 1 egg, and in 63 experiments, right, plus the one that you already ran, you can figure out which of those floors below 64 is critical. If it survives from 64, you've got 2 eggs, and you've only got 64 floors that you have to investigate, right? So that's going to be better than 128. So the question is, how do we figure out what the guaranteed maximum number of experiments is that you need for a given number of floors and eggs? And it's going to turn out we can do this like we've been doing knapsack and rod cutting. We can set this up as a function that can be calculated using other values of the function. So we'll play around with that tomorrow. We'll also look at red-black trees tomorrow. So I'm going to cut out, if you've already done your surveys for 215 and 222, you can take off. Otherwise, I'd like you to take the time to fill those in.